we prove the first part of our proposition. The first part. The condition is that f is differentiable at a, b. We want to prove f1 and f2 are differentiable at a and b respectively. This is the our mission to prove. So by the condition capital F is differentiable, there is how to no. We know that let eta hk to be capital F a plus h minus b plus k minus f a b minus the derivative of f at a b acting on the vector hk. Okay, this is the increment of capital F approximated by the linear map of hk. So the differentiability of capital F at AB means that this limit hk goes to 0, eta hk divided by the norm of hk is 0. Okay, now to prove f1 differentiable at a and we want to prove that the derivative of f1 at a acting on h is equals to the derivative of fab acting on h0. This is the result. We will prove it to be true. Okay, so to prove this statement, the differentiability of f1 at the point A and also the formula for computing the derivative of f1 at A, the derivative of f1 at the point A. The derivative of f1 at A is P by a matrix where H is in Rk. H in Rk, Rm, H in Rm. Therefore, this multiplication is vector in Rp. The right hand side also a vector in Rp, because the derivative of f at AB is P by m plus n. Well, this is an m plus n dimensional vector, so their multiplication is also a vector in Rp. So this is the formula for computing the derivative of f1. Of course, by definition, once f1 is differentiable at a, then actually this f1a is the partial derivative of our f with respect to x at the point ab. Okay. Now to prove this statement, we estimate we consider the limit of f1 a plus h minus f1a. This is the increment caused by the h for f1. Then minus the anticipated derivative, that is f1 f derivative of fab at h0. Okay, we estimate this. Maybe no. What's this? This is precisely f by the definition of f1. Remember, our f1 x is f xb. Okay, so using the definition of f1, our this quantity is a plus hb minus f1 sorry, not f1. FAB, F1A is FAB, then minus F prime AB H0. Okay, what's this? So this is precisely the eta. Now, this is eta H0. In the expression of eta here, in the expression of eta here. When k is 0, take k to be 0, we obtain the vector inside the norm of in this. Okay. So our this quantity is precisely the norm of eta h0. Therefore, this means f1 a plus h minus f1 a minus f prime a b h0 divided by the norm of h. But the norm of h is precisely the norm of h0. The norm of h in Rn is precisely the norm of h0 in Rn plus n. So when h goes to 0, this goes to 0. And this is precisely h0, the norm of h0, eta h0. So because eta divided by the norm of hk, in particular k, take k to be 0, the limit is 0. Therefore, we conclude that this right hand side goes to 0. This right hand side goes to 0. So because this limit is 0, we see that this goes to 0. So this goes to 0 means that f1 is differentiable at the point A, and also the derivative of f1 at the point A is given by this. Okay? Given by this f prime AB acting on h0. So in conclusion, we have proved that f1 is differentiable at the point A, and the derivative of f1 acting on h is the derivative of f at AB acting on h0. Similarly, you can prove that f2 is also differentiable at the point B, and the derivative of f2 at the point B acting on k is the derivative of f at AB acting on 0k. So the derivative of f at AB acting on hk, this can be written as the derivative of AB acting on h0 plus 0k. hk is h0 plus 0k. Now the derivative of capital F at AB is a matrix, or it is a linear map. So this multiplication is precisely f prime AB h0 plus f prime AB 0k. But the first term here is precisely the derivative of f1 at the point A acting on h. Similarly, the second term is the derivative of f2 at the point B acting on k. Here. Okay. So now by the definition of the partial derivative, we know that the partial derivative of capital F with respect to x at the point AB is precisely the derivative of f1 at the point A. So this is the partial derivative acting on h plus the partial derivative with respect to y also at the point AB acting on k. So this prove our equality in the statement in the first part of our proposition. We already established the differentiability of f1 and f2, and we also get the equality at the last line of this page. That is here. Okay? That is this equality. Okay? So we have proved the first part of the proposition. Now, the second part of the proposition, the equality stated in the second part of the proposition here, because we have already in our proof of the second part, we already proved that capital F is differentiable at AB. Therefore, we can apply the result of the first part to get this equality. Okay, so in conclusion, this proposition has been proved. Okay, now having proved this proposition, we are ready to state and prove our important theorem, the implicit function theorem. So I will state it because this is a generalization of the previous Dini theorem. So I will state the theorem here first. This is the implicit function theorem. Suppose U is an open set in Rn, and V is an open set in Rn. Open. And we have a map F defined by over U cross V to Rn. And also we have a point AB is a point in U cross V. So the assumption is that FAB is 0, and also the derivative, partial derivative of capital F at the point AB, the partial derivative of capital F at the point AB. What's this? Here, U is m-dimensional, V is n-dimensional. So the partial derivative of F at AB is the derivative of the map Y map to FAY. Okay, this map is our F2. The derivative of this F2 at the point B is the partial derivative of capital F at AB with respect to Y by our definition. So because F2 is a map from n-dimensional Y, the image is also n-dimensional because our map is mapped into Rn. The dimension of the target space of our capital F is the same of the dimension of V, which is n-dimensional. Okay, so the F2, to define the partial derivative of capital F with respect to Y, the F2 is a map from n-dimensional open set V to n-dimensional space. Therefore, the derivative of F2 at B, that is the partial derivative of capital F at AB, is an n by n matrix. N by n matrix. So for this n by n matrix, we can talk about the determinant. We assume that the determinant is not 0. So this is the condition imposed on the map F. In addition to the differentiability, we assume that F is a C1 map. I forgot to mention that it is C1. Capital F is C1. In addition to the differentiability, that is, it is C1, we also require that capital F is 0 at the point AB. And also the derivative with respect to Y at the point AB is an invertible matrix. That is, the determinant is not 0. So this is the condition on F. Then the conclusion. What's the conclusion? Then there are open set in Rn containing A. That is, O belongs to this notation we introduced in the when we study the inverse function theorem. This notation means all the open set in Rn containing the point A. So O belongs to this set means that O is an open set in Rn containing the point A. Okay. Similarly, this is containing A, and also another open set containing the point B in Rn, and also a map phi from O to omega. This map is C1. such that, of course, we need to have O cross omega containing in U cross V, and the following are the essential conclusion of the theorem. The first is that phi A is B. The second is that for any x in O, our capital F x phi x is 0. This means this means we solve for y from fxy 0. We solve for y equal phi x. Therefore, this map phi we declare its existence is an implicit function of x. So why this theorem is called implicit function theorem. Okay. So in addition to these two conclusions, we also have the third conclusion about the uniqueness. If xy belongs to O cross omega is such that capital F xy is 0, then y must be phi x. Fxy is 0. We also have fx phi x is 0. So this third statement is the uniqueness statement. Then y must be equals to phi x. Okay. So this is the statement of the implicit function theorem.